Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 1884, titled Egg Drop with 2 Eggs and N Floors. This is a fascinating problem that explores optimization strategies and problem-solving techniques involving edge cases and constraints. Let's dive in. In this problem, you are given 2 eggs and a building with N floors. Your task is to determine the minimum number of moves required to find the highest floor from which you can drop an egg without it breaking. Let's break this down further. If you drop an egg from a floor higher than the threshold floor, it will break. However, if you drop it from a floor at or below the threshold floor, it will remain intact. Each move involves dropping an egg from a specific floor, and you can reuse any egg that doesn't break. The challenge is to minimize the worst-case number of moves needed to identify the threshold floor. The input to this problem is a single integer, n, which represents the total number of floors in the building. The output is the minimum number of moves required to achieve this goal in the worst case. Let's look at the first example. Here, the total number of floors, n, is 2. The output is 2 moves. Here's how it works. First, drop the first egg from floor 1. If it breaks, the threshold floor is 0. If it doesn't break, drop the second egg from floor 2. If the second egg breaks, the threshold floor is floor 1. If it doesn't break, the threshold floor is floor 2. In this scenario, the worst-case number of moves to determine the threshold floor is 2. Now consider the case where n equals 100. The explanation for this case is shown on the next slide. When n is 100, the minimum number of moves required is 14. The reasoning here is based on using an optimal approach to minimize the worst-case number of moves. You use the first egg to systematically narrow down the range of possible threshold floors, dropping it from specific floors in a way that progressively reduces the uncertainty. Then, the second egg is used to test each remaining floor within this narrowed range. By carefully selecting the floors to drop the first egg, you can ensure that the worst-case number of moves is minimized, and in this case, you only need 14 moves to find the threshold floor. Lastly, let's consider the case where n equals 1. Here, there is only one floor, so the solution is straightforward. Simply drop the first egg from floor 1. If it breaks, the threshold floor is 0. If it does not break, the threshold floor is 1. In this scenario, only one move is required. Additionally, there are constraints to keep in mind. The number of floors, n, ranges from 1 to 10,000, and you have exactly 2 eggs. The goal remains to minimize the worst-case number of moves, even for large inputs like n equals 10,000. The algorithm must also handle edge cases efficiently, such as the smallest input of n equals 1, intermediate values like n equals 10 or 50, and the worst-case scenarios involving the maximum input size. When tackling the problem of determining the critical floor with 2 eggs and n floors, several approaches can be considered. The brute force method is the most straightforward. Here, we begin at the first floor and drop the first egg incrementally from each floor until it breaks. Once the first egg breaks, the second egg is used to test the floors below the breaking point one by one. While this method guarantees a solution, it is highly inefficient for large values of n, as it requires testing up to n floors in the worst case, leading to an O(n) time complexity. Another approach is to use binary search. The intuition here is to divide the floors into halves, starting at the middle floor and dropping the first egg. If it breaks, the second egg tests the floors below sequentially. If it doesn't break, we repeat the process in the upper half. While this approach reduces the number of drops for the first egg to O log n, it still requires additional linear scans for the second egg, making it suboptimal for this problem. Both these methods fail to fully optimize the use of the limited 2 eggs, especially for larger buildings, highlighting the need for a more efficient strategy. To address the inefficiencies of the brute force and binary search methods, we can turn to dynamic programming. The DP approach is built on the principle of minimizing the worst-case number of moves while effectively utilizing both eggs. The idea is to evaluate 2 subproblems for each drop. If the first egg breaks, we test the floors below with the second egg, and if it doesn't break, we test the floors above with both eggs. The goal is to minimize the maximum number of moves across these 2 scenarios, adding 1 for the current drop. To achieve this, we define a DP table where DP, M, K, represents the maximum number of floors that can be tested with M moves and K eggs. Using the recurrence relation DP, M, 2, equals DP, M1, 1, plus DP, M1, 2, plus 1, we iteratively calculate the minimum number of moves required to test all N floors. The base cases simplify the problem. With 0 moves, no floors can be tested, and with 1 egg, we can only test up to M floors in M moves. By iterating through the DP table, we find the smallest number of moves M such that DP, M2, is greater than or equal to N. This method ensures that we optimize the use of both eggs while minimizing drops. Dynamic programming emerges as the optimal choice for this problem because it directly addresses the limitations of the previous approaches. The brute force method, while simple, is prohibitively slow for large N and fails to leverage the second egg efficiently. Binary search, while faster, doesn't make full use of the 2 eggs, leading to unnecessary drops in the worst case. The DP approach, on the other hand, is specifically tailored to minimize the worst case number of moves while maximizing the utility of both eggs. The key breakthrough here lies in recognizing that the problem can be divided into smaller subproblems based on whether the first egg breaks. By dynamically calculating the optimal floors to drop eggs at each step, we avoid both the inefficiency of sequential testing and the rigidity of binary division. This approach not only reduces the number of moves but also adapts to the constraints of having only 2 eggs. When comparing trade-offs, DP outperforms both brute force and binary search in terms of efficiency and optimality, making it the best strategy to solve the problem. In summary, the dynamic programming approach provides the most efficient solution for the egg drop problem with 2 eggs in N floors. By leveraging the constraints and minimizing the worst-case number of moves, this strategy ensures that we determine the critical floor with the fewest possible drops. Unlike brute force, which is too slow, and binary search, which doesn't fully utilize the second egg, the DP method optimizes every move. This makes it the ideal solution for balancing efficiency and practicality in this challenging problem. In this problem, we are tasked with identifying the highest floor of a building from which you can drop an egg without it breaking. You are limited to using 2 eggs, and your goal is to minimize the number of drops required in the worst-case scenario. To build a foundation for solving this problem, let's first explore the brute force approach. The intuition here is straightforward. You start testing floors sequentially, beginning from the first floor. If the egg doesn't break, you move to the next floor and repeat the process. The moment the egg breaks, you know the critical floor is 1 level below the current floor. To implement this, you initialize the process with 2 eggs and set the current floor to 1. You then proceed step by step, dropping the first egg from each floor, checking if it breaks, and continuing until you either find the critical floor or reach the top of the building. While simple, this approach is highly inefficient, especially for tall buildings with many floors, as it may require a large number of drops in the worst case. After determining that the first egg has broken, we now need to pinpoint the exact critical floor. To do so, the second egg is used to test each floor, one by one, directly below the breaking point of the first egg. The critical floor is identified as the highest floor where the egg doesn't break. Finally, the result is returned, which includes both the critical floor and the total number of egg drops needed. While this brute force approach is straightforward, it's not practical for larger buildings due to its inefficiency. Let's now consider a more optimized solution. If only 1 egg is available, the best strategy is a linear search, as there's no way to test higher floors once the egg breaks. In this scenario, you start testing from the lowest floor and drop the egg sequentially until it breaks, recording the highest safe floor along the way. This method guarantees that you'll find the critical floor, but it's still inefficient since it requires testing each floor individually. Once the critical floor is identified using the single egg, the result is returned, including both the floor number and the total number of drops. Now, let's explore a significantly more efficient approach when 2 eggs are available, the triangular number search. This method strategically minimizes the maximum number of drops required in the worst-case scenario by using a decreasing step size. To begin, you calculate the initial step as the largest triangular number less than or equal to the total number of floors. This ensures that even in the worst case, the number of drops will be minimized. You then drop the first egg from this calculated step. If the egg doesn't break, you decrease the step size and continue testing higher floors. However, if the egg breaks, you switch to the second egg and test floors sequentially below the breaking point to find the critical floor. This method strikes a balance between efficiency and accuracy, reducing the total number of drops required. After identifying the critical floor using the triangular number search, the result is returned, including both the floor number and the total number of drops. This approach offers several important insights. First, while brute force is simple to implement, it becomes impractical for buildings with a large number of floors. The binary search method is optimal when you only have one egg, but it cannot be directly applied when multiple eggs are available. The triangular number search, however, is designed to minimize the maximum number of drops in the worst-case scenario, making it an ideal solution for this problem. The implementation relies on simple variables such as current_floor to track the floor being tested and drops to count the number of egg drops. No additional data structures are required, as the problem primarily involves straightforward calculations. In terms of complexity, the brute force method operates in O(n), while binary search achieves O log n for a single egg. The triangular number search is even more efficient, with a complexity of O(n) due to its linearly decreasing step sizes. To ensure the robustness of our solution, it's essential to consider edge cases. For example, if the building has only one floor, a single drop is all that's needed. If no eggs are available, the problem is unsolvable. For scenarios with a high number of floors but only a few eggs, optimized strategies like the triangular number search are crucial to minimize the number of drops. Another challenging case arises when the critical floor is located at the very top of the building. In this situation, both eggs may need to be used, leading to the worst-case scenario in terms of drops. To illustrate how the triangular number search works, consider a building with 10 floors and 2 eggs. You start by dropping the first egg from floor 4, following the triangular number sequence of 4, 3, 2, 1. If the egg doesn't break, you proceed to floor 7. If it does break, you use the second egg to test floors 5 and 6 sequentially. This process continues until the critical floor is identified. Finally, the output of the algorithm provides the critical floor and the total number of drops required. For example, in a building with 10 floors and 2 eggs, the critical floor might be floor 6, and the number of drops required might be 4. This demonstrates the efficiency of the triangular number search approach, which carefully balances step size and minimizes the total number of drops in the worst-case scenario. By leveraging this optimized method, we can solve the egg drop problem effectively, even for large buildings with a high number of floors. This concludes our deep dive into the algorithm, showcasing how different approaches can be applied and optimized to address the problem under varying constraints and edge cases. The problem is about finding the minimum number of egg drops required to determine the highest floor from which an egg can be dropped without breaking. You are given 2 eggs and n floors, and the goal is to minimize the worst-case number of drops. In this solution, we use a mathematical approach to minimize the worst-case number of drops. The idea is to strategically test floors such that the sum of the first k drops covers all n floors. This ensures that even in the worst case, we minimize the number of drops. ###code explanation. 1. Initialization*. Steps is initialized to 0. This variable keeps track of the number of drops needed. Cumulative_floors is initialized to 0. This variable represents the sum of the first k floors being tested sequentially. 2. While loop*. The loop continues until the cumulative_floors, total floors tested so far, is greater than or equal to n, the total number of floors in the building. In each iteration, steps is incremented by 1, representing the next floor to test. Cumulative_floors is updated by adding steps to it. This represents testing the next batch of floors in the sequence. 3. Return statement*. When the loop ends, the steps variable contains the minimum number of drops required to cover all n floors in the worst case. ###example walkthrough. If n equals 10, the function works as follows. Step 1, test the first floor, cumulative_floors equals 1. Step 2, test the third floor, cumulative_floors equals 1 plus 2 equals 3. Step 3, test the sixth floor, cumulative_floors equals 3 plus 3 equals 6. Step 4, test the 10th floor, cumulative_floors equals 6 plus 4 equals 10. The loop stops, and the result is steps equals 4. This approach ensures optimality in terms of minimizing the worst case number of drops, as it uses the minimum number of tests required to cover all floors up to n. This is the Java implementation of the LeetCode problem number 1884, egg drop with 2 eggs in n floors. It follows the same logic as the Python version, using a greedy approach to find the minimum number of steps required to determine the critical floor. Key differences include Java's explicit type declarations and the class structure. The method iteratively adds steps until the total exceeds or equals the number of floors, ensuring the solution is efficient and concise. To solve the problem of determining the minimum number of steps required to find the critical floor with 2 eggs and 2 floors, we start by defining our initial values. Initially, the number of steps, or attempts, is 0, and the cumulative floors we can check is also 0. In the first iteration, we increment the steps by 1, making it 1. Adding this to the cumulative floors gives us 1. Since the cumulative floors are still less than the total number of floors, which is 2, we proceed to the next iteration. In the second iteration, we increment the steps again, making it 2, and add this to the cumulative floors, which now becomes 3. At this point, the cumulative floors are greater than or equal to the total floors, so we've met the condition. Therefore, the minimum number of steps required to determine the critical floor for 2 floors is 2. Now, let's explore the case where we have 10 floors. We start again with the initial values of steps set to 0 and cumulative floors to 0. In the first iteration, we increment the steps by 1, making it 1, and add this to the cumulative floors, which becomes 1. Since 1 is less than 10, we continue. In the second iteration, we increment the steps to 2, and the cumulative floors increase to 3. Again, 3 is less than 10, so we proceed. In the third iteration, we increment the steps to 3, and the cumulative floors now total 6. This is still less than 10, so we move forward. In the fourth iteration, we increment the steps to 4, and the cumulative floors reach 10. At this point, the cumulative floors are equal to the total number of floors, so the condition is met. The minimum number of steps required to solve this case is 4. Next, let's tackle the larger example with 100 floors. As always, we start by initializing steps to 0 and cumulative floors to 0. We then begin iterating. In the first iteration, we increment the steps to 1, and the cumulative floors become 1. In the second iteration, steps increase to 2, and cumulative floors rise to 3. In the third iteration, steps are 3, and cumulative floors total 6. In the fourth iteration, steps become 4, and cumulative floors reach 10. Continuing, steps increase to 5, with cumulative floors at 15. Then, steps are 6, and cumulative floors total 21. In the seventh iteration, steps reach 7, and cumulative floors are 28. Finally, in the eighth iteration, steps become 8, and cumulative floors rise to 36. At this point, the cumulative floors are still less than 100, so more iterations are needed. We continue from where we left off, with steps at 8 and cumulative floors at 36. Incrementing steps to 9 gives a cumulative total of 45. Then, steps increase to 10, and cumulative floors become 55. At 11 steps, the cumulative floors are 66. At 12 steps, the total reaches 78. When steps are 13, the cumulative floors rise to 91. Finally, at 14 steps, the cumulative floors reach 105, which exceeds the total of 100 floors. This satisfies the condition, and we can conclude that the minimum number of steps required to solve the problem with 100 floors is 14. When analyzing the time complexity of this solution, the goal is to minimize the worst-case number of egg drops needed to find the critical floor using 2 eggs. The approach relies on a cumulative sum strategy, where we incrementally test floors until the total number of tested floors equals or exceeds the number of floors, and mathematically, we calculate the cumulative sum as the sum of the first step's natural numbers, 1 plus 2 plus 3 and so on, which simplifies to steps plus 1/2. To determine the minimum number of steps required, we solve the inequality steps plus 1/2 equals n. Rearranging this leads to a quadratic equation, and applying the quadratic formula gives us steps equals -1 plus sqrt, 1 plus 8n/2. This means the number of steps is proportional to the square root of n, which establishes the time complexity as O, sqrt, n. Breaking down the operations further, we start with the initialization of two variables, steps and cumulative underscore floors, which is a constant time operation, O1. The main computation happens inside the while loop, where each iteration increments steps by 1 and updates cumulative underscore floors in constant time. Since the number of iterations is proportional to sqrt, n, as derived earlier, the total time complexity of the loop is O, sqrt, n. Moving to the space complexity, the algorithm only uses two integer variables, steps and cumulative underscore floors. There are no additional data structures or recursive calls involved, so the space usage does not depend on the size of the input n. Both variables occupy constant space, making the overall space complexity O1. To understand the efficiency of this approach, let's compare it to a brute force method. In the naive solution, we would test each floor one by one, starting from the first floor all the way up to floor n. In the worst case, this requires n egg drops, leading to a time complexity of O(n). The current solution, however, drastically reduces the maximum number of drops to O, sqrt, n, by leveraging the mathematical properties of cumulative sums. This approach is optimal because it minimizes the number of attempts required to determine the critical floor, even in the worst case. By incrementally increasing the step size, we maximize the efficiency of the first egg, leaving fewer floors to test with the second egg. This ensures the solution is both mathematically and practically optimal for the given constraints of two eggs. Now let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, if n is very small, such as n equals 1, the algorithm completes in a single iteration, giving it a time complexity of O1. For typical values of n, the time complexity is dominated by the cumulative sum calculation, which grows proportional to sqrt, n. This gives an average case complexity of O, sqrt, n. In the worst case, when n is very large, the number of iterations increases proportionally to sqrt, n, resulting in the same O, sqrt, n, complexity. To mathematically justify this, we revisit the inequality steps 2 plus steps 2 n equals 0. The dominant term in the solution of this inequality is sqrt, 2n, which grows asymptotically as O, sqrt, n. Lower-order terms like steps and constants are negligible in comparison, confirming the overall time complexity is O, sqrt, n. When solving the egg drop problem, there are a few common mistakes candidates tend to make. One major pitfall is not optimizing for the worst-case scenario. Many focus on minimizing the average number of attempts, but the problem often emphasizes minimizing the maximum attempts in the worst-case scenario. Neglecting this can lead to suboptimal solutions, especially for edge cases. Another error is misunderstanding the problem's constraints. Some assume fixed values, like 2 eggs and 100 floors, rather than recognizing the problem's generalized nature. This lack of flexibility can result in solutions that don't scale well to larger inputs, such as 10 eggs and 10,000 floors. Lastly, candidates sometimes incorrectly apply binary search, assuming it's the optimal strategy. While binary search minimizes the number of floors tested, the goal here is to minimize egg drops, which requires a more nuanced approach. Understanding these distinctions is crucial to crafting an optimal solution. Another frequent issue is overcomplicating the recursive solution. Many candidates struggle to set up a clean recurrence relation or forget to implement memoization. Without memoization or a bottom-up dynamic programming approach, the solution becomes inefficient, often resulting in exponential time complexity. Additionally, edge cases like 1 floor, 1 egg, or 0 floors are frequently overlooked. These scenarios are critical for validating the robustness of your solution. For instance, with 1 egg, the only strategy is to test each floor sequentially. Ignoring these edge cases can lead to logical errors that undermine the correctness of your approach. Addressing these common mistakes will significantly improve both the efficiency and reliability of your solution. To succeed in an interview setting, there are a few key insights to keep in mind. First, recognize that this problem revolves around reducing the search space. The optimal solution is all about balancing the trade-offs between the number of floors tested and the number of egg drops. Communicating your thought process clearly is equally important. Interviewers value candidates who can articulate how they derive the recurrence relation or transition to dynamic programming. Testing edge cases is another crucial step. For small inputs, like one egg or one floor, logical errors often become apparent. Lastly, be prepared to analyze both time and space complexity. For example, the dynamic programming approach typically has a time complexity of O, k*n, where k is the number of eggs and n is the number of floors. Demonstrating a solid understanding of these aspects will leave a strong impression. This problem also has connections to several related problems on LeetCode, which can help deepen your understanding. For example, Problem 887, Super Egg Drop, is a more generalized version of this problem. Problem 472, Concatenated Words, and Problem 279, Perfect Squares, are related due to their dynamic programming strategies and similar recurrence patterns. Exploring these problems can give you additional insight into how to approach variations of the egg drop challenge. As for alternative approaches, one option is brute force, where you incrementally drop an egg from each floor until it breaks. While this is simple to implement, it has a time complexity of O(n²) for n floors, making it inefficient for larger inputs. Understanding the trade-offs of brute force can help you evaluate its practicality in different contexts. Dynamic programming is a more refined approach to solving the egg drop problem. In this method, you build a DP table where DP, k, n, represents the minimum number of attempts needed with k eggs and n floors. This approach has a time complexity of O, k*n, making it suitable for small to medium-sized inputs. However, it can be memory-intensive for very large inputs. Another advanced strategy is mathematical optimization, where you derive formulas to minimize the worst-case number of attempts. This method is highly efficient, with a time complexity of O, k*log n, but it's more complex to derive and implement. Both approaches have their strengths and trade-offs, and understanding when to use each can be a powerful tool in solving similar problems. Thank you for watching. We've covered the key concepts and takeaways from this problem. Remember, egg drop problems are excellent practice for dynamic programming and optimization. Don't forget to like, share, and subscribe for more problem-solving tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!